beamer.
Roesch.
It is. I know. It's going to be bad. It's not Roesch. That would be the worst.
Roesch. Most people say Roesch.
Yeah. Yes, the spotlight is quite bright up here.
Yeah.
Oh, we're good. Okay, great. So we're going to continue talking about neural ODEs with Elisabeth Roesch.
Thank you. Can everybody hear me? Thank you for your talk, Jesse. I'm going to continue talking about neural ODEs. Now I'm going to focus more on the fitting procedure in Julia. Everything I'm using is in DiffeqFlux. As a background and a short introduction to myself, I'm a theoretical systems biologist, so I will focus more on how we use it in our research. So just as a short motivation of why we actually use neural ODEs, we have a lot of, a huge part of systems biology is dynamical systems, and very often we observe nonlinearities. So as you can see here, 3 examples of a protein over time. In the middle you can see the ECG, or some zooplankton over time, in a lake. You can see all looks fairly nonlinear. And the problem that we're having there is that we want to model it, and very often easy methods don't work for that. So the 3 commonly used approaches to model nonlinearities in our field are direct modeling, differential equations, or machine learning methods. And from the left to the right, the prior knowledge that is required to use those methods decreases. So in an ideal world where you know everything about the system that you're curious about modeling, you have a function f, and that describes your dependency perfectly. So I just give you a time point 5, and you can return to me the product abundance at that time moment. So very often, obviously, that's not the case. That's the ideal world. But it would be very nice to always be there, because the interpretability of the models is very high. So if we shift a bit further to the right side, we are differential equations. So in those scenarios, we maybe still know something about the structure of the system. So you know protein A influences protein B, and then there's a protein C, and that leaves the cell. So you can still define that structure with an ordinary differential equation or a stochastic differential equation. And then maybe you have some unknown parameters, but you can use Bayesian approaches to infer them. And the nice thing about this approach is that you still can tell the biologist, okay, this parameter that I just inferred relates exactly to the degradation rate of a certain protein. So as a biologist or a medical doctor, that's obviously very, very nice, because you still have got that interpretability. And this is the area that I'm most of the time working. I didn't say. I'm a first-year PhD student. So most of my time, I used to work in differential equations in that area. But now we are focusing more on systems where we don't even know that structure. So, and this is where we thought about using machine learning models to directly model with deep learning models the output of the system. But the problem there is that, first of all, you need a lot of data, obviously. And second of all, you lose interpretability. And in our field, it's really nice to have as much interpretability as possible. And neural ODEs are somewhere in the middle of those two, because when you define your neural net not as the output of the system, but the gradient, you still learn something about the structure of the system, and that gives us the possibility to still have more interpretability. So that's where neural ODEs come to use. So I'm going to start with ODEs as well. So a normal ODE, you have your species U, and the difference over a certain time interval, and you have a function f that describes this gradient. But if we are now looking at neural ODEs, we substitute that function f by a neural net. And that can be any neural net you want it to be. And the way that works in DiffeqFlux is that you have your du dt as a chain object. And in those layers, the nice thing is that you can use whatever function you want. So in this case, the first layer, you have this x mapped on x to the power of 3. So you can include prior knowledge in the structure of your ODE. And that's a very nice feature for us as systems biologists, because sometimes we do have this prior knowledge, and we can include that here. So that's very nice. Excuse me, I still have the old syntax as well. Or so you define it as the flux parameters afterwards. Okay, so once you have defined your neural net, we need to train it, obviously. So we want to go from the left picture to the right picture. In the left picture, you can see two species we observe over time, and the prediction in the beginning with just the random parameters. And then on the right side, you can see that the prediction really aligns well with our observation. And the question, obviously, is how do we get from the left to the right picture? And that's what I want to talk to you today about. So I want to compare 3 different training strategies. So the first one will be an ODE model with the L2 norm as a loss function. The second will be a collocation model with the L2 norm of the gradients as a loss function. And the third one will be a mixture between the two of them. Okay, so the first one, if we start on the left upper corner of the figure, you can see we have our neural net and the different layers. And it's our gradient. And it's like we have a parameter combination P. And we want to minimize now the error to our observation. That's visualized on the right side of the figure. And for in one training epoch, we have the current prediction of the neural net, du dt, for the parameter combination P. And we can build on the fly now an ODE with this gradient and solve the ODE with any gradient you wanted. You can have it as an input for the function, whatever you want the solver to be. And then we will calculate the distance, just a standard L2 norm between the observation and the the current ODE solution. And then you get one value for that, and that's the one that you want to minimize, right? And then you use any optimizer that you want to sample your new P and repeat. And hopefully you will finally end up in a nice global minima. So that's the first training strategy. The second one is the collocation model, originally suggested in 2008 by Liang and Al. So the way this one works is that before we actually start the training procedure, we have to do some prior calculations. So we do have our observation in blue on the upper left corner. And then we use local regression to estimate not just the solution, but also the first derivative. And by doing so and using that in our actual training procedure, we avoid a repetitive ODE solving, which takes a lot of time. So this lower part of the figure is actually in the training itself, so that's after the pre-calculation. So you've got your estimated derivative and the estimated species, and you can use those two then to minimize the error. But this time, as an error, we do not compare the actual output of the system, the species, but we compare the gradients directly. So that's a bit of a difference. And the idea for this approach is that we approximate something, we avoid using the ODE solver. So we're doing this because we try to save time. That's the motivation for that method. And the third training procedure is this mixture procedure. So we start with a less precise approximation-based approach, and then we do the more precise L2 norm with the ODE solver. And the idea is that, maybe you see that in the middle part, stage 1, you can see we get in the general area, and then in stage 2, we really try to go down and minimize. So these are, this is the theoretical background of the 3 training procedures. So now to results. My results are structured as follows. We first look at simulated data, so I pretend to know, like I know a certain ODE, simulate observations, and then pretend not to know it and guess it again. And we will look at one simple example, which you probably will recognize if you read Chris' original blog post. And on this example, I will compare a bit of the performance, like accuracy-wise and convergence-wise. And also I will discuss a bit the effect of data size on the different methods. And as a second simulated data example, I will use a system that is more relevant to me as a systems biologist, the Pol Oscillator. And then I will actually look at some experimental data, some heart rate over time, and a specific signaling pathway in the cell. So the simple example looks like this. You've got the two species over time. This is the true ODE function up there. You can see it like the core is like this cubic function. And we just solve it. So this is the observation that we are dealing with. And the structure from the neural net that I'm using for this procedure will be the one that you've seen actually in the chain object before. Maybe you recognize it. So you've got the cubic function as the first layer, and then you've got two dense layers with 100 parameters each. As an activation function, I use the hyperbolic tangents, and as an optimizer, I use Adam with a learning rate of 0.1. Okay, so these are the three fits we get for the three different training strategies. So on the very left, you can see it's like a very nice fit with the L2 norm. In the middle, you can see especially on the lower part of the green line, you can see there's a big gap to the observed data, like a fairly big gap. And the right one is, again, like fairly nice. So, I mean, I couldn't tell if like the left one or the right one is actually the better fit. So these are like the fitting results. And this is probably the nicer thing to look at. It's like how our loss value drops over the training. So if you look just on the very left figure, where you can see the ODE model in blue, you can see after about 250, so we do 1,000 training epochs in total, and after 250, you can see that the loss is already like fairly converging, and like after that, it doesn't change a lot anymore. And in the middle part, let's first look just on the orange line. I should have locked that probably. You can see that it's very flat and it doesn't change a lot anymore. And whereas like but this is like the collocation loss. So if you remember from the theoretical background section, I'm actually comparing the differences in gradients, so the L2 norm of the gradient. And that is like hard now to compare to the left value because it's just like a different value, right? So I just picked like a few training epochs, like every 50th or something, to calculate the actual distance to the observation at the current state. But that is not information that the model gets actually in the beginning. So that's just for us as a control. So you can see, how the L2 value drops. And on the very right, you can see the mixture procedure. So you can see first we did 5,000 training epochs with the fast one, the collocation model, and then we did 100 with the L2, the ODE model. And you can see that it doesn't look like much on this side probably, but that is the difference from this picture to this picture. So this is only collocation, and this is collocation with afterwards the ODE model. And that's like just these 100 epochs at the end. So the figure that I showed you before was always like, how does the loss behave over the training epochs? But we didn't really measure any time. So in this figure, I'm actually comparing real time. So you can see on the x-axis, you've got just like time in seconds. I should have wrote that. And how the error drops. So if we first look at the orange line, that's probably the easiest. That's your collocation model and how the collocation loss drops over time. So it's this nice line. And the line in green is now the translated L2 control. And the interesting part is now the blue point is the actual ODE model. So you can see this orange thing is a line, and those is like a scatter. And I did that because the orange line is like 3,800 loss evaluations whereas the blue are just like 17. So and it's like in time. So you can see that the collocation is a lot faster. And even though maybe that doesn't look that drastic of a difference, or like, I mean, it is a difference, obviously. But if you, like, these are 17 training epochs of the ODE model. If you go to the left figure, like where the 17 training epochs, you're still like not close to converging or anything. But you can see here, the collocation model already has converged. So that's a very important figure. Okay, then the next thing I want to discuss is how the data size affects the different training strategies, and or like the two models actually. And by data size, I mean the number of observations we have in one time series. So you can see in orange is the collocation, and in blue is the L2. And this is just how long does one training epoch take. And you can see, like, before, I always chose, like, a data size of, like, 30. And you can see the distance is not that significant. I mean, there's a key distance, but it's not that big. But if you increase your data size, that distance gets a lot bigger. Obviously, this is, like, heavily depending on, like, exactly which solver you're using and, like, how you specify it. But just as a general idea, the collocation, as we do the whole, like, regression before the actual training, it's not in each training epoch that you have that difference. That you have that time that you need for the ODE solver. So the more data you have, the bigger actually this difference gets, or like the more significant it gets. And obviously that scales. Yeah. And yeah, like in the figures that I showed you, like we are on the very left side. So this is actually a favor case for the L2 model, the ODE model. Okay, the second simulated data example that I wanted to show you is the Pol Oscillator. So second order differential equation system. And I chose that one because it's relevant for biological research. So you use it, for example, in models for like the activation potentials of neurons and stuff like that. And these are two observations. So on the left, it's like the exact solution at just certain time points. And on the right, it's like I added some technical noise because I know already I want to do experimental data afterwards, and I expect technical noise, obviously. Okay, so the two fits for those two data sets look like this. This is the collocation model now only, and because I wanted to investigate how that is affected by noise. And you can see that even with the noise term, you can like still capture the original structure. Yeah, obviously you can increase that noise. Yeah. This is how, again, the loss drops over the training, so in training epochs. Yeah, you can see with the noise, like, it actually dropped, like, in the beginning it's very similar, but then it goes, like, further up, so it doesn't go down there anymore, and that's due to the noise. Okay, and then to the experimental data. Before I go into it, I have to make a few disclaimers or assumptions that we have. There's obviously technical noise in experimental data, and that can get quite drastic depending on like the discipline. The second thing is, and probably the most important one, the time series data is very, very expensive to us. Like, I mean, if we have like 30 time points, you have to do experimentally 30 times in the lab. That can be very, very expensive and time consuming. And sometimes it's even impossible. So sometimes an experiment requires for the cell to die. So how do you get a second time point? It's just like not possible, right? And the third thing is that we often expect the underlying system to be very complex. So there's this trade-off between like data density and complex system that we're constantly struggling with. So the first experimental data set that I want to show you is like not a crazy one that goes like this, but just like fairly static one and just like a few outliers. So you can see the heart rate over time. Like once it's like during a run, and one is like in the recovery. Do I need to say anything? No. And these are the two fits that we get. So you can see on the left side, the prediction catches the points, but it doesn't like get all the small ones, but it's like in the right area. Whereas on the right, you can see that it actually does like, it's not that flat as over there, so it does like linger out to catch other points. And we can also look again at like how the loss evolves over time. So you can see, for example, down here, the this is the collocation model again. you can see like it drifts off, but it comes back again. So you can see there are these two little orange peaks, but it comes down again. So that's very nice to see that it drifts back in the right area. And the last data set that I want to show you is a bit of a more complicated one. And yeah, this is molecular biology area more, and this is the area where I mostly work in, actually. And what we see here is we have got data of protein complexes over time, and those are involved in the signaling pathway for the growth of a cell. And so you can see there's a growth factor in the very left corner. It's like accepted by a receptor on the cell membrane, and then there's this downstream reactions where you have these two protein complexes, MEK and MEK-ERK. And yeah, so these are very important for like how the cell grows, like to describe that. So we do have measurements of those two protein complexes over time, and you can see that in the beginning there's this peak. And we can already expect that will be hard to fit. And but this peak is very important for us as biologists because we know, so in these systems, when the peak is in the beginning or versus when there's a transient movement, that is the difference of like, does the cell just like divide and like becomes like the same cell twice, or does it differentiate actually? So it's really important for us to catch that peak. Yeah, and the data set is by Sarah Filippi, a future colleague of mine. And yeah, these are the fits that I get right now. And this is the loss evaluation right now. So this, I want to like end with this example. And yeah, so we're not there yet where we want to be, but we have some ideas of like problems that cause this non-fit. And yeah, I mean, it looks like, if you look like that, in the beginning I was like fairly excited because I thought maybe if I just train longer it will converge somewhere, but it did not. But yeah, we do have some ideas of like where the problems are, and I'm happy to discuss them further later on. And just to give you a little outlook, like where we want to go with this research. So as I said, normally we do like differential equations for as a modeling technique because of the interpretability. So this is like area of mechanistic modeling. But now we switch to systems where we just don't know the structure to use the machine learning models. And the idea is that we always like combine those two and try to let them communicate with each other. We call this hybrid modeling, and that's like the bigger outlook of my PhD. And yeah, specifically, like it's really interesting to look at the inferred vector fields of the neural nets and the neural ODEs to see like where they converge to, and like if we can see like fixed points or something like that. And that's other people from the DiffeqFlux community work on that, and it's very, very interesting. Obviously, I didn't do that work alone. I want to thank a few people who've worked on that with me. First of all, my supervisor, Michael Stumpf, and my second supervisor, Hee Jung, Chris, for mentoring this specific project. Obviously, the Julia community. That's really amazing, like the feedback you get, it's really cool. And my research group in Melbourne and London. And my code is available on GitHub if you are interested. And these are the most important references. Thank you very much.
Convenient. So you showed a lot of things on the training of your neural ODEs, but
Yes.
not a lot on testing.
Yes.
So what happens if you train it on one person's heart rate and then try and use it to predict another person's heart rate, or train it on a portion of the time series and ask it to predict the rest of the time series?
Right.
Have you done anything like that?
I mean, what we get out of the model is a continuous prediction, right? So we have just give it a few training points, and we predict on a continuous,
interpolated, right?
So I also try, like changing the initial conditions and try. Yeah, I mean, I did a lot of that for the running examples, like to start as somewhere else and see how it goes. I think it's not about changing the person, but more like the initial condition, because that's like the input layer. So that's interesting to look at. And I think, yeah, David did a lot of work on that. So maybe that's like to see like if you change the initial conditions, like how that works.
You'd like to know whether you're learning any kind of meaningful dynamics, or all you're doing is interpolating the data you're getting. Right?
I think, yeah, for us it's very interesting to look actually. I mean, the point where I'm coming from is that we have no other option to model this dynamic. So, and if you fit the neural net, you get a vector field out of it. And that tells you a lot of like where you're converging to, and that's the interesting part for us.
I think that the other interesting thing is that the information is in the dynamics of the phase space, right? You're not actually training with respect to time, but with current state, point in phase space. So if you actually loop back around, then it will have learned that it keeps on looping back around, right? Even though it looks like extrapolation in time, it's actually still just interpolating within phase space. And so you'll actually be able to tell further in time, just perfectly fine, whereas some other methods which are actually trying to learn time series won't be able to do that.
This is just my observation. For example, for your curve fitting of the
Yes.
spikes,
Yeah.
maybe you could change the problem instead of, because you'll notice that there's most of the points are in the non-spikes, and if you're training the thing,
Yeah.
of course it will always be biased with non-spikes. So maybe instead of having that problem, you can change it to predicting the duration when the
Sorry, say like the position of the
predicting the duration when the peak occurs,
Yeah.
instead of just curve fitting.
Yes,
And I think
yes.
you will have much better
Yeah.
spike detection.
Yeah, yeah. Thank you. Yeah, that's a good comment.
Go ahead and set up your laptop. This was the last question.
I maybe missed a slide, but so are you assuming that the dimension of the system is known? So, like, are you assuming that you observe all the relevant states of?
Sorry, I didn't get that. Sorry,
Okay.
I was sorry.
So, are you assuming that you know the dimension of the system? I mean, are you assuming that all the states are observed?
That's a very interesting question, especially like especially like the last example, this one. There are other species. Like, are you talking about the input dimension? Like, I mean, so we do have like other inputs
Dimension of the ODE.
Yeah. So we do have other species that we do actually observe, and that's like something that Chris and me were just talking before about. Like that's like maybe we actually need those species in order to be able to infer the dynamics, because like we need them, otherwise it's not like inferable.
So they are observed or just?
We do have the data, like the data exists, but I don't have it yet.
Okay.
But I hope I will get it. Yeah.
So my question is would it be beneficial to add like non-observed, like hidden?
Or like
cells?
non-observed ones. I haven't thought about it, but yeah,
So
it
for
could.
example, you can fit from the Pol Oscillator
Yeah.
without observing X dot.
Yeah.
And
Okay.
and I'm wondering if you can do that. It means collate method.
Yeah. It's. I mean, I haven't tried it, but it sounds interesting. Yeah.
Okay.
Yeah. Thank you.
Thank Elisabeth again.
Thank you.